In this video, let us explain the idea of expectation, mean of a value, and standard deviation, as well as its connection with the regression line of a bivariate data. Let us assume x and y to be representing two random variables. Connected with any statistical event. Okay. We would like to find out the correlation between these two variables x and y. It should be assumed here that this capital X and capital Y may represent any statistical bivariate distribution also, and it may represent some random variables also. We have two types of dependence. One is y on x, where x is assumed to be independent and y depends on x, and the other is x on y, where it is assumed that y is independent and x depends on y. Okay. Now you all know that the mean value may be represented as expectation of x, and let us denote m01 as expectation of y. Okay, and we may represent as sigma 1 as root over mu 20 to be the second moment, or we may write it as expectation of x minus m10 whole square. Okay, these are formal notations where you should remember that this is standard deviation and square of it is variance, where we actually measure expectation of x minus expectation of x whole square. So obviously mu 02 will be sigma 2, which is the variance of y. Okay, sigma 2 will be mu 02, and it will be root over expectation of y minus m01 whole square. Here we would also like to introduce mu 11, which is actually covariance, and we represent it as x minus expectation of x, or say m10 into y minus expectation of y, which is m01. So this is actually mu 11. Okay, and with this terminology we can find that the condition of expectation of y minus alpha x minus beta whole square may be represented as some function of alpha and beta only. And this expectation of y minus alpha x minus beta whole square is to be minimized with respect to these two variables alpha and beta, which gives the best linear regression, or rather I should say the linear relation between this y and x, or rather these two random variables. And this is minimized to give us the best fitted straight line representing x and y, or the tabular data or the bivariate data, whatever you say. Okay, so let us see that how can we. Let us first write this like this. The expression y minus alpha x minus beta, we would like to rearrange it in this way. Y minus, now what is the expectation of y? This is m01. So we want to club here like this. So since we have get this m01 extra, so we will have to balance it and write plus m01. I am keeping it for the last term. We would also like to balance x with the expectation of x, which is m10. So this is x minus m10. Okay, understandable? So we have added this alpha m10 and subtracted this, and here you have this minus beta. So to balance them, we should write plus m10, this is balanced, minus alpha m10, this is also balanced, and we have minus beta already there. So it turns out to be like this. Okay, so I hope this is clear. Let us put a first bracket here. So here we have actually three terms, this minus this plus this. Now we would like to see about this whole square effect regarding these three terms. I would like to write this as expectation of y minus m01 whole square, okay, plus alpha square expectation of x minus m10 whole square. Then we have the 2ab term, this and this. So the 2ab term will give us minus 2 alpha expectation of y minus m01 and x minus m10. Fine. And then we have obviously this term only, m01 minus alpha m10 minus beta whole square. Since this is a constant term, so expectation of this term is actually the term itself. And what about the other terms? The other terms becomes 0. Why? Because we know that due to this definition, we know that expectation of x minus m10 is expectation of x minus m10, and it is 0. And we have expectation of y minus m01 follows from this definition that this is also 0. So when we calculate the other product terms, they are all equal to 0 and we are left with only these three terms. Actually a square plus b square plus c square, and we have minus here, so 2ab term that exists. And the other terms where this is multiplied with this, it becomes 0, and when this is multiplied with this, this also becomes 0. So this is understandable that we have only these three terms as expectation of y minus alpha x minus beta square, which is a function of alpha and beta only. And now if we look at this, we may write it as, this is whole square, so we may write it as this first one, mu 02, f alpha beta is mu 02, plus we have alpha square mu 20, this one, minus we have 2 alpha mu 11, okay, and this is a intact term, we are getting it like this. So this is our f alpha beta. Accepted? And we would like to minimize this so as to best fitted regression relation. So you should take the derivative of f with respect to alpha and with respect to beta. So when you take the derivative of this with respect to alpha, we get 2 alpha mu 20 minus 2 mu 11, and here we have minus m10. sorry, minus actually 2 into m01 minus alpha m10 minus beta into m10, because we are taking the derivative of alpha, the derivative of f with respect to alpha. So here we have 2 alpha in mu 2 naught, here we have minus 2 mu 11, and here derivative of this turns out to be like this. Okay, so this is 0. And what about del f del beta? Let us wipe this out and write this equation, cancelling this 2 and adjusting. We have alpha mu 2 naught minus mu 11 minus m01 minus alpha m10 minus beta into m10 equal to 0. Okay, and when you take the derivative of del f with respect to beta, del f del beta, this is f, and we are taking that. We see that there is no beta in these three terms, so the only term we get is 2 into m01 minus alpha m10 minus beta into minus 1 actually, which is 0, and this 2 and minus 1 get cancels out, and we have this. Okay, and from here we can easily get the value of alpha and beta both, isn't it so? We have, since this is one relation, and this reduces this relation to, this is actually 0. So this reduces this relation to alpha equal to mu 1 1 by mu 2 naught. Isn't it so? This is 0. So this reduces to, so we have only this two relation to find alpha and beta. So beta may be alpha is this, and beta may be represented as m01 minus alpha is this, so mu 11 by mu 20 into m10. Okay, okay, clear? So with this notation, where m10 is expectation of x, m01 is expectation of y, sigma 1, sigma 2 are the variance on standard deviation as we write, and mu 11 is this termed as covariance. We have this value of alpha and beta, which gives the best regression line. Okay, now we can reduce this further with this concept of correlation coefficient. Okay, rho, which is covariant xy by sigma x, sigma y, we may write it as mu 11 by sigma 1, sigma 2, and we can see, replacing the mu 20 by sigma 1 square, we may easily write the regression line of y on x as, using this concept of correlation coefficient and sigma 1 and sigma 2, we may easily write it as y equal to m01 plus rho sigma 2 by sigma 1 into x minus m10. This is the regression line of y on x. Okay, just see that we have used this value and this value only here. So this is regression of y on x, and conversely we can write the regression of x and y. Okay,